Today we introduce some very important terminology which is fundamental to the study of linear algebra. I will say a lot of the homework type exercises in this section, well, the type of calculation we do, we could have done already, but it's the language that's new and understanding concepts, and they're quite important. Subspaces in Rn. In fact, I mentioned what a subspace was last time. So let us just recall a subset W of Rn is a subspace of Rn provided zero needs to be in W. If you have two things in W, then the sum is this was called closed under addition. And finally, if say V is in W, then KV is in W for any scalar K. This one was called closed under scalar multiplication.
Well, what is a subspace in Rn if you want to think about it geometrically? This first example is animated. I'm taking all multiples of the vector 1, 2. And you see, this gives us a line, line through the origin, and that's an important thing to point out. Generally in R2, 0 is a subspace. Then you have lines that go through the origin. And then you have all of R2. Those are the only subspaces. If we think moving into R3, this first example, this is a subspace of all x, y, z, such that x equals y. And this is a plane through the origin. If you needed to prove that, let's see, where's my cursor? Here it is. If you needed to prove that this set is a subspace, you could easily show that the 0 vector satisfies the first two coordinates are equal. If you have two that satisfy the first two coordinates are equal, then their sum does as well. And then if you have one vector that the first two coordinates are equal and you multiply by k, it satisfies that also. So you could go through those three parts of the definition if you so desired for this set. It's a plane through the origin, and all planes through the origin in R3 are subspaces, but not every subset of R3, or generally Rn, is a subspace. So let's look at two examples that are not. Okay, here we go. Look at this. This is pretty. This is the set where x times y times z is 0. And, well, this is a union of planes to the origin. It's the plane where x equals 0 with the plane with y equals 0, and then the plane with z equals 0. They all take their union, and this is what we are looking at. This is not a subspace. Certainly 0 is in this set. Well, and even if you took something in there multiplied by a constant, you would be back in the set. But the problem is vector addition. So for example, if I look here, V and W are both in this set because multiply the coordinates, you get 0, but you take their sum and you get 1, 2, 1. It's not in their set. So this green subset of R3, not a subspace. And then we'll look at one more. Okay, this is the set of all vectors in R3 such that the first coordinate is 1. Well, it's a plane, right? And so you might think it looks like a subspace until you carefully look at the right angle or you just look at what's defining this set. But you see here that the origin 0, the 0 vector, well, it's not on the plane, I should say. So this set is not a subspace. Okay, so the subspaces in R3, 0. Lines through the origin, planes through the origin, and then all of R3. As you move to higher dimensions, well, you have 0, lines through the origin, planes through the origin. For example, 3 spaces through the origin, things like this. These are the subspaces.
The way we think about subspaces in terms of, for instance, the last video and today and moving forward is in terms of the span subspaces W of Rn. And then you take a span of a bunch of vectors. Maybe I won't write them, I'll just write them like this. V1, V2 to Vm, okay? This is precisely, these are equivalent. So this is precisely what a subspace is. Every subspace of Rn is the span of a bunch of vectors in Rn. Maybe I should write that. These are in Rn. And similarly, if you take a bunch of vectors in Rn and you take their span, and this means, as we discussed last time, you take all linear combinations of the vectors, that's a subspace. Okay? So these are what the subspaces are. Okay? They are spans of vectors. As I mentioned, a lot of the calculations we did last time, we're going to understand what we were doing more after today. So last time we had the following. This was one of the examples we did. 1, 2, 5, 3, 6, 15, 0, 1, 0, and then 5, 16, 25. And I wrote that the image of A is the span of 1, 2, 5, 0, 1, 0. And that we did several examples of finding vectors for that span the image and the kernel, and both of them we started by row reducing the matrix and figuring out where the pivots were, or I should say leading ones. Same thing as pivots. But also, just by definition, the image of A is the span of the columns. Let me put this down now that I wrote the matrix down. It is, by definition, the span of the columns. So both the image and the kernel, as we discussed last time, are subspaces. And the image is, by definition, the span of the columns. Oops, there's a 16 here. These two corresponded to the columns that had leading ones. And I said you didn't really need to include the other ones. They were redundant. Well, I'm going to make all that precise today. But why don't we need this one and this one? So let's get more specific as we develop more terminology and things like this. Why don't I need those in this? Why don't I need to include them? Or equivalently, why is this span the same as this span? Well, let's look at these vectors. This vector equals, well, it's 3 times this one. Okay? So if you just take the span of, definitely it's in the span of here, it's even just in the span of the very first vector. This one is already in this set, so you don't need to list it again. Right? Now what about this one? Okay? This other one. 5, 16, 25. Well, I see 0 here, so it's going to have to be 5 times the first one. And this gives me 5. It gives me 25, but it only gives me 10 here. So then I can just add 6 times this one. And you see this fourth vector is a linear combination of these two. So this fourth vector is also in this span, okay? So this collection of vectors that we found just by row reducing the matrix and figuring out where the leading ones were, pulling the columns out of A, and you'll have something like that in the homework for this section. This was sort of a better choice of spanning set because it doesn't have all these redundant. This one was redundant because it's already in here, and this one was redundant. It's already in here too. Okay, well, now let us get into what the language that makes everything I just said and a lot of what we discussed last time easier. And these are the concepts of linear independence and linear dependence and basis of a subspace. We have a collection V1 to Vm of vectors in Rn. Okay? Now let me get into, as I was starting to define, I will say a vector Vj is redundant if it can be written as a linear combination of the sort of previous vectors, so of this collection Vi such that I is less than j. Okay, or I could have said 1 is less than or equal to I less than j. It's fine like this. So if it can be written as a linear combination of the ones that come before. And here you see, for instance, we see that this, even though I have it here. I just erased what was above. This one is a linear combination of just the one before. This one's redundant. And this one is a linear combination of this one and this one. This one is redundant. Okay, so these two, in this set of 4 vectors, this one and this one, as we have demonstrated, are redundant. And this was even the word I used yesterday. I just didn't write this on the board. Okay. Now comes for the notion of linear independence, the collection, I'll just say V1 to Vm, is linearly independent if it contains no redundant vectors. Contains no redundant vectors. Now I'm going to erase as I continue to define things. So what I was doing, in particular when we were working with the image, which by definition is the span, well, it's the subspace that is the span of the columns of a matrix. And by pulling off the columns that corresponded to leading ones, I was removing the redundant vectors so that what was left in the examples of yesterday, and you could do in your homework, well, for this section even, what's left is just the linearly independent collection, or a linearly independent collection that still spans. Okay. And then let me underline what I defined. Linearly independent, and then it is linearly dependent Well, if it is not linearly independent, but you could also say it like this, if it contains at least one redundant vector. One redundant vector. Okay, well, this is very nice. Let's do this example, which will lead us to another way to think about linear dependence and independence. So here, well, I'm not given exactly what the matrix is. In fact, I don't even know its size, except I know it's, say, n by 4. But I do know one vector that's in the kernel, okay? 1, 2, 3, 0 is in the kernel of A. And I want to show that v1, v2, v3, v4, these 4 vectors in Rn are linearly dependent, which means, at least at the moment, definition, we need to find one of them that's redundant, right? So one of these needs to be written as a linear combination of the ones that come before. Okay, so how are we going to do this? Well, let's go back and think about what it means to be in the kernel. Okay, well, we know A times this vector is 0. Okay, and how do we multiply a matrix times a vector? Well, linear combination of columns. So this means that v1 plus 2v2 plus 3v3, well, plus 0v4 is 0. And now I can use this to solve, well, let's see, I'll get v3 as a linear combination of v1 and v2, just like this. So that means that, well, in particular, so then, I don't know where to write, then, well, 3v3 is minus v1 minus 2v2, and we just divide by 3. Minus a third v1 minus 2/3 v2. So what we see here is that v3 is a linear combination of v1 and v2. Vector v3 is redundant. Okay, thus this collection v1, v2, I'm not going to use this blue anymore, v3, v4, this is linearly dependent. Okay? Very nice. Well, what I want to focus on from this example is this part. And I forgot I had, it's the 0 vector. You add a bunch of vectors in Rn, you get a vector in Rn. Okay, very nice. Well, I want to focus on this. This has a name. If you take a collection of vectors and you take some linear combination of them and you set it equal to 0, as I have here, this is what's called a linear relation in our text. Okay. And this one is what's called, I'll add even more to it, a non-trivial linear relation. And what does that mean? Well, I'm about to write, but it means that not all of the coefficients are 0. This coefficient's 1, this one's 2, and this one's 3. So they are not all 0. It's a non-trivial linear relation. Well, let me erase some, and I'm going to write, so you'll notice though, now it's half erased, or maybe a third erased, but what I was going to say, you'll notice the way I was able to write v3 as a linear combination of 2 of the vectors that came before was because of this, right, being a non-trivial linear relation, because this equation allowed me to write v3 as a linear combination of ones that came before. And so we can characterize linear independence and linear dependence in terms of these linear relations. So in terms of taking some linear combination of the vectors, setting it equal to 0, things like this. Okay. So now again, suppose I have V1, V2 to Vm. These collection of vectors, these are linearly dependent if and only if there exists a non-trivial linear relation. And as I write this, I'm going to define it. So what is a non-trivial linear relation? Well, it's some C1 V1 plus C2 V2 plus C M Vm equals 0 with not all Ci 0. Okay, just as we saw in that example. And even if we went back, so let's back up even further before I say anything else. If we go back to this example, let's take these vectors. It was what? 1, 2, 5. And then we had 3 times it, 3, 6, 15. And then we had this one. And then we had 5, 16, 25. Okay, I'm surprised I remember that without looking at my notes. Okay, so these, right, this one was redundant, this one was redundant, and let's remind ourselves why. If I call this V1, V2, V3, V4, then we had, and this is how we started today, we had that V2 was 3V1, and we also had that oh, yeah, we're okay. That's right. I thought I had my indices off. It looks okay. Okay, and then we had V4 was 5V1 plus 6V3, right? And okay, these are dependent because this one is redundant. That alone gives you dependence, but then you add another redundant vector and you still are linearly dependent. But if I wanted to think about it in terms of these non-trivial linear relations, it comes exactly from this. What gave us these redundant vectors, the non-trivial linear relations, well, from this one I get 3V1 minus V2 is 0. There is 1. And as I said, just having this one alone, immediately dependent, linearly dependent. But we have another one, which is that 5V1 plus 6V3 minus V4 is 0. And again, I need my hats. Okay, so this is sort of going between redundant vector, where you have one vector written as a linear combination of some of the others, and this characterization where you have some non-trivial linear relation among the vectors. Now I will comment that, don't know where to erase, maybe here, every collection of vectors, every collection, V1, V2 to Vm of vectors has what's called the trivial solution or linear relation, which is that 0V1 plus 0V2 plus 0V3, 0Vm, is 0, Okay, this is the trivial. Everything has that linear, dependent, independent. All of them. Every collection of vectors has this trivial linear relation because you take 0 times a vector, you get 0. Add up a bunch of zeros, you have 0. So that's fine. But if you are dependent, then you have one of these non-trivial relations, linear relations. And I will say, now let me make a comment about some other texts, because I'll make a comment about how some other texts sometimes define independence, which is in terms of these linear relations. So sometimes the text will define, you can take as an alternate definition. Maybe I should write it that way. Alternate definition would be that V1, V2, V3 to Vm are linearly independent. Provided, so if you have C1 V1 plus C2 V2 out to Cm Vm equals 0, then C1 is C2 is C3 is out to Cm is 0. So this is a definition I've seen in other texts, and it's equivalent to the one in our text about linearly independent. It says you don't have any redundant vectors. And this says that, well, it's a if-then, but if you have some linear combination of vectors, the collection equals 0, it must be the case that all of the coefficients are 0. And sometimes this can help you spot a collection of linearly independent vectors by thinking of it in this framework. And this is a very important definition. Okay, a collection V1 to Vm is what's called a basis for a subspace W, we'll say of Rn, although I'm not using Rn per se in this, it's just some subspace. Okay, the subspace provided, well, there's two things here. The first one is if you take the span of, maybe I'll do it this way, the span of V1 to Vm, you get all of W. And the second thing is that V1 to Vm, there should be Vm, is linearly independent. Or maybe I'll say R, that these vectors are linearly independent. Okay? So what we did yesterday, and this is one reason why I said a lot of the calculations that come up in this section, okay, there's two things in linear algebra and both are important. There's a theory, understanding what you're doing, and then there's the calculations. A lot of the calculations we were doing yesterday of finding this, what was I calling it, like this smallest set of vectors that would span the image. Well, we were finding a basis for the image of a matrix. Okay, so when you see those in the homework for this section, now you know how to do it, right? I just didn't have that language because we hadn't talked about all this yet. But when you remove redundant vectors from a collection of vectors, you do not change the span, as we saw in some of the first examples, right? If you remove something that's already in the span, then you don't change it. So you the process then of we were finding this smallest vectors we could by pulling the columns out of the matrix that corresponded to where the leading ones were in the reduced row echelon form, and this found a basis. Okay, we will definitely be talking about more of that. But this is what a basis is. You have to both be spanning and be linearly independent. As I mentioned at the start of today's topics are fundamental to the course, and the notion of linear independence and linear dependence is fundamental to the topic of linear algebra. And so before we do a few examples, I'd like to explore this notion of linearly independent just a little bit more. Okay, so suppose we have these vectors in Rn. What can we do? So we can form a matrix where we put these in the columns. Now, this might make you think of this example that I did where I just told you something in the kernel and we used that to find a redundant vector, and that led us into discussing linear relations. And this is kind of how our discussion is going to go. Okay, well, then this C1 V1 plus C2 V2 out to CM VM equals 0 can be written as, well, you can take the matrix times this vector of coefficients, and this would equal the 0 vector, right? Because look, what is A times this? Well, A times a vector, linear combination of columns, so it will be C1 V1 plus C2 V2 all the way out to CM VM. Okay, so this can be written as follows, and so we see that this collection V1 to VM are linearly independent. This means that, well, we only have the trivial solution to this. Linearly independent. Let me go back to my black. If and only if this, well, if the only solution to this equation or linear relation is the trivial, okay, it says that the kernel of A is just 0. Right? Now this is also, well, if and only if, when is the kernel of A 0? It means you have no free variables. And this means that the rank of this matrix needs to be the number of columns, M. Okay, well, what is this now? Okay, we're going to say one more thing, and then we're going to move into some examples. I think I'm going to say one more thing. I feel like a lot of this, I'm just translating the same thing into lots of different language, but it's important to understand the theory of what's happening here. Okay, now this we discussed last time. This matrix, now I'm going to have to step back and think about the size of this matrix. This matrix is N by M. If it's rank M, this means we must have, I'll go to red. You have to have at least that many rows, because we know this is the number of leading ones, and every leading one, well, you can only have one per row, and you can only have one per column at most. Okay, so if this is the number of leading ones, you have to have at least that many rows. So we must have n bigger than or equal to m. And so what this says, and this is a nice conclusion, and well, I'll mention it again when we do some examples. Immediately we get the following, is that if we have that m is bigger than n, okay, then any collection of m vectors in Rn is dependent, linearly dependent. Okay, so the largest number of linearly independent vectors you could possibly have in Rn is n. Okay, if you have more than that, if you have n plus 1 vectors in Rn, immediately linearly dependent. We know this. I have my board subdivided into group 1, group 2, and they all have something in common. Well, let's see. One side dependent, one side independent. And let's figure out which, then we will discuss. Well, immediately, everything over here is going to be linearly dependent, and we will discuss. This side is the dependent side. Uh-oh. I just barely fit that. Everything over here, literally independent. Maybe I'll write it up here. Okay, well, which side do we want to start with? Maybe the dependent side. What's wrong with this first one? Well, immediately, anytime, so my comment on the first one is that 0 cannot be in a linearly independent collection. Of vectors. It cannot, because, well, what would be if you wanted to, there's a couple of ways to see it. If you wanted to have some non-trivial linear relation, you can just take anything. 5 times this vector equals, I'll write it over here. 5 times v2 is 0. Well, there's a non-trivial linear relation, right? Or you can write 0 as 0 times this vector. And so, in fact, that would be the redundant one, right? 0 will never be in a collection of linearly independent vectors, ever. Okay, so now we understand this one. Maybe I will erase, I'll erase this part. Okay, very nice. Now, what about this one? Well, this one we see is dependent because this second vector, v2, I'm not sure what I was doing there. v2 is 3 times v1, the second one. So this is dependent. Oh, I didn't close my parentheses on this one, or my bracket. Immediately we see this one is dependent because we have 1, 2, 3, 4 vectors in R3. Can't have that. The largest you can have, the largest linearly independent set in Rn will have n vectors. And this has 4, which is bigger than 3. Okay. And now what about this last one? Here we have 3 vectors in R4. Technically, 3 vectors in R4 could be independent, but if you notice, if this is v1, v2, and v3, v1 plus v2 gives us v3. v1 plus v2 equals v3. Right? Add these 2, add these 2, add these 2, add these 2. So this would be the redundant one, or you could translate this into a non-trivial linear relation amongst the vi's if you wanted to. All of these are dependent. Now how about independent? Well, this is one vector. This is the easiest one to see. It's not the 0 vector. It's independent just by itself, okay? But now both of these, to see that they're independent, maybe I'm going to erase this one so that I have space to write. Both of these, at least in my opinion, what is the easiest way to see that they're independent is this other characterization about having no, well, if you have a linear relation amongst the vectors, then you must have all the coefficients be 0. So the only one is the trivial. So if you, and this works, I should say, a lot of times when you see zeros carefully placed. So for this one, if I had C1 plus C2 plus C3 equals 0. Okay, well, this corresponds to a linear system, right, where we get C1 plus C2 plus C3 is 0. And then we have 2C2 plus 2C3 is 0. And then we have 3C3 is 0. Now, without even going to reduced row echelon form, I could put these in a matrix and transform that to reduced row echelon form if I'd like. But just thinking, this last equation gives me C3 is 0, and then I move up to this one, and I would be able to get C2 is 0. Once C2 and C3 are both 0, you can conclude C1 is 0. So from this, you get C1 is C2 is C3 is 0. Okay. Now, this one is similar. The zeros are carefully placed. Let's call this V1, V2, V3. If I had C1, V1 plus C2, V2 plus C3, V3 equals 0, it's going to lead to 1, 2, 3, 4, 5 equations in C1, C2, and C3. But the very first one here, it says that C3 is 0. And then which one can I use next? Once C3 is 0, let's use this one. It says minus C2 plus 10 C3 is 0. We then also get C2 is 0. Once I have that, well, for instance, I could use this one, or really any of them. It says 2C1 plus 8C2 is 0. C2 is 0, so C1 is 0. Once I have C3 and C2 0, then any of them will work, but we get that the only linear relation amongst these must be the trivial one, namely C1, C2, C3 is 0. And this type of thing is an argument that you can use quite often, especially, for instance, here, if you look at the matrix, if we put this in a column, you see it's upper triangular, right? And this is what the careful pattern of zeros that I used here to conclude that the vectors were linearly independent. In this example, well, it looks like the two columns or two groups of examples I had on the board. We just have a collection of vectors. We want to know if it's linearly independent or dependent, but it's not so obvious. I don't have the vector 0 appearing. One is not a multiple of another. What else? This is in R4. I don't have 5 or more vectors in R4. If you have 3 vectors in R4, maybe it's independent, maybe it's dependent. You can't have both. And then I don't have any zeros carefully placed like in the last two examples. So we have to think differently. So what can we use? Well, remember, we can look at the matrix where these are the columns. And then if we can find something in the kernel besides just 0, you find some non-zero vector in the kernel of that matrix, this will give you a non-trivial linear relation. Well, another way to say that is it will give you that one of the vectors is redundant. Okay, so let's do that. We know this is what we practiced last video. We know how to find the kernel of a matrix. In fact, we don't have to even find the whole kernel. We just need to find one non-zero thing in the kernel. But to do this, we will perform elementary row operations. So let's see. I want to take minus row 1 and add it to all the other rows. So here, add it to row I for 2 less than or equal to I less than or equal to 4. And this will give me zeros all underneath this leading one. The first row remains the same. And then I get 0, 2 minus 1, and 4 minus 1. And then, well, these will all be zeros. And then I have 3 minus 1, 7 minus 1, and then 4 minus 1, and 10 minus 1. Okay, the next step would be, I have leading 1. I want to get zeros underneath, and I can do that in one step. I take minus 2, row 2, add it to row 3. I take minus 3, row 2, add it to row 4. Okay, then what do we have? Row 1, I have not changed. Row 2, I have not changed. Row 3, look, this is now 0, 0. And then row 4, you take minus 3, row 2, add it to row 4, we get 0 and 0. One more step. If I add minus row 2 to row 1, what do I have? Well, reduced row echelon form is what I will have. I will have 1, 0, minus 2. I will have 0, 1, 3, and then I have 2 rows of zeros, right? Okay, well, let's talk about what we know, or what we have discussed today. There's a few equivalent ways you can go about justifying independent or dependent. One, well, literally independent would be if this matrix, if the kernel was 0, and we would get dependent provided this matrix, there's something non-zero in the kernel. Similarly, if we have amongst these 3 vectors, if we have a non-trivial linear relation, we get dependent. Or if one of these vectors is redundant, we get dependent. Okay, those are all really saying the same thing, but let's go back to here, reduced row echelon form. We see we have, well, leading 1, okay, and then free variable. So we will in fact have something in the kernel. And what will this be? Okay. Well, let's just find one thing rather than putting a T and writing all like a general vector in the kernel. Let's find one thing because that's all I need to make my justification. So to do that, I can, for instance, just set the free variable to be 1. This equation says x2 is minus 3x3 or minus 3. And then the top equation says x1 is 2x3 or 2 times 1. So this vector here, 2 minus 3, 1, this is in the kernel of, let's say I call this matrix A up here. If this is A. Okay, so this, okay. We're done. We know the answer. Or we're done if we want to be, but I will make a few more comments here. If we want to be done, we are done right here. Dependent, because here's a non-zero vector that's in the kernel. But also, another comment that I will make, maybe I'll erase some of these steps in getting ourselves to, reduced row echelon form, but I'll leave my matrix A. Okay, what this gives us in the kernel is it gives us a non-trivial linear relation, because look what it says. It says 2 times 1, 1, 1, 1 minus 3 times 1, 2, 3, 4 plus 1, 4, 7, 10 is 0. And so this is what I was referring to as a non-trivial linear relation. So again, this would be a second way to justify that these 3 vectors are dependent. I guess the third way to justify would be just to move this third vector over to this side, and you can see that this one here is redundant. So this is sort of, in this one example, we're seeing all the different ways that, or some of the ways that I discussed what dependence is. And it's all really the same thing, it's just different ways to think about it. I like this example because it connects, well, it's a little abstract, which is okay, but it also connects what we're doing now with some things we've been thinking about in recent sections. So here, n is different than m, so A and B, neither one are square. A is n by m, B is m by n. Well, we can multiply A times B, and when we do, we get an n by n. So we have a square, and we are assuming that A times B is the n by n identity. And this is called a left inverse. Now, what did we talk about just a few videos ago? We had, if A is square, n by n, and B is square, n by n, once you know A times B is the identity, you know immediately BA is also the identity, and A is B inverse, and B is A inverse, right? But here, you don't have all of that because these are not square matrices. And it's just called a left inverse, that when you multiply like this, you get the identity. What we can show, and we will show, let's prove the columns of B are linearly independent. Well, what we're going to do before I start the proof is, because I'm dealing with columns of B, I've got to column something. So let us say that B is W1, W2, out to W, we have n columns. And then, just to set myself up, because I know the way the proof goes and I'm going to need this in part of it, what are the columns of AB, or what is AB? AB is, well, I know what the columns are. Each column of A times B is A times a column here. So the first column is A, W1, and the second column is A, W2, out to A, WN. Okay, now I'm ready to start to prove that this collection of vectors is linearly independent. This problem is very similar to one in the exercises, but it's one that is not assigned, but it's very nice for us to do now. Okay, well, let's assume C1 W1 plus C2 W2 out to Cn Wn is 0, and we want to show C1 is C2 all the way out to Cn is 0. This was what I mentioned that some other texts have as the actual definition of linear independence, and it's definitely equivalent to our definition of there being no redundant vectors. That concept we have discussed, but I like this way of proving a collection of vectors is independent because it's an if-then. It says if you have something like this, then you have to show all the coefficients are 0. So this formulation is nice in arguments like this. Okay, well, I am just going to, I have this is an equation. It says this sum is 0. I'm just going to multiply both sides by a. Except I'm going to change the order of the sides. So first, a times 0 is 0. That's true for any matrix A. And then if I'm going to apply a to this side. So I have C1, W1 out to Cn, Wn. Now here, one of the properties of matrix multiplication, or equivalently of linear transformations, is that you can break a sum and you can pull scalars outside. This was the linearity that we have discussed both for matrix multiplication and linear transformations. So I may write this as C1a W1 plus C2a W2. Okay. And this, maybe I'll put a reason here, this I'll write using linearity. Well, now we're in great shape because look, this is vector. Let's underline the vectors I'm going to refer to now. This is column in A times B, column in A times B, all the way here. So now I'm looking at the underlined vectors. They are columns in this matrix product. But A times B is the identity, and the columns of the identity are literally independent. That's quite easy to show. Well, because the kernel of the identity is 0, for example. Okay. So as A, B equals identity on N, we know that this collection is linearly independent. And so we can conclude C1 is C2 out to Cn is 0, just like this. This would be the end of our proof when we have shown that the columns of B are linearly independent. Okay. Now, I think the other part of the homework, which I did not present, asked about the columns of A. Maybe I'll let you think about that. It's not going to be the same statement, I'll tell you that right now. I'd like to make one more statement that's, well, we will prove it, so we're going to end on a bit theoretical of a note. But I think that's fine, especially because, as I mentioned, the sort of calculations that come up in the homework, or finding a basis for the kernel of a matrix, finding a basis for the image of a matrix, or showing that finding a redundant vector in a collection of vectors, things like this. We're ready for that, right? We have discussed both in the last video and this one. Okay, so I would like to say one more really important thing, and it's the following. Suppose we have, this is one reason why we love bases. So suppose V1 to Vm is a basis for W, a subspace of Rn. Well, then every vector in W can be written uniquely as a linear combination of these vectors. In fact, I think if you read in your text about this, it's really a if and only if. So if you have a collection of vectors, and for every vector in your subspace, you can write it uniquely as a linear combination of those, then in particular you can conclude that that collection is a basis. But I really just want to talk about this direction, although both directions are true. And this uniquely part is one reason why this is very nice. Okay, so let's prove this, and then I think we'll be about finished for the day. The proof. Well, what am I trying to prove? I'm assuming I have this basis for W. Then every vector in W can be written. Okay, so I need to take a vector in W. Let V be in W. Okay, well, first of all, what does it mean to be a basis? This means this collection spans W, number one, and I'm going to use that first. And then this collection is linearly independent. Okay. As of this collection is W. This marker is not doing so well. Let me try this blue. We may find or we may write V is C1 V1 plus out to C M V M for scalars CI. Okay, so this is because these vectors span the subspace. That means the subspace consists of all linear combinations. So in particular, V is a linear combination of those vectors. That's this first part. So far, I have this part, can be written. But this part is an important part of the statement, uniquely. And this part I don't have yet, right? So how do you show something you've already shown exists? How do you show it's unique? Well, you could just assume you have another thing of that form, show it had to be that, right? If you assume you have something of this form and then show it had to be equal to this one particular, then it's unique. So here we go with that part. Okay, so now assume that V is just some linear combination. And then we need to show, and this will be the end of this argument, that DI is CI for 1 less than or equal to I less than or equal to N. Once we show this, we're finished. Okay, well, we can just write 0 in a clever way. We can write 0 as V minus V. I guess so far that wasn't all that clever. V minus V is without a doubt 0, but now I'm going to say this one minus this one. So then this is C1 minus D1 V1 plus out to CM minus DM VM. Okay? But this collection, V1 to Vm, is a basis. In particular, this collection is linearly independent. So as this collection, or as the vectors are linearly independent, we know the only solution to this equation, or equivalently, there's only one linear relation among those vectors. It's the trivial one. It's the one where this is 0 and this is 0 and all the ones in between, they're 0. So I was writing and talking at the same time. Independent. I must have been saying something about the solution. Independent. Okay. As these vectors are linearly independent, we can conclude CI minus DI equals 0 for 1 less than or equal to I less than or equal to N And now we just add, for example, di to both sides. This is what I wanted. Show this, okay? So in fact, and we used both. This part, we had a basis, and then I was saying every vector in the vector space can be written uniquely. And there's two parts to that. The can be written came from the fact that the basis spans. And then uniquely came from the fact that the basis is linearly independent. So you really need, in order to make this observation, or just generally to be a basis, you really need both. You must be linearly independent and you must span.